Hey everyone, in this video I'll introduce a commonly used gas law known as Charles' Law. Here's a quick refresher on gas laws in general. These are mathematical laws that summarize relationships that we observe between gas variables like pressure, temperature, and volume. These mathematical models help us make predictions about what's going to happen with gases in real life. In this video we'll cover just one of these gas laws known as Charles' Law, first published by this guy right here. So Charles' law states that the volume of a gas is directly proportional to the temperature of that gas as long as the pressure stays constant. What exactly does that mean? Well, a direct relationship between these two variables tells us that if the temperature is increased, the volume of that gas will also increase, or the opposite, if the temperature goes down, the volume of that gas will also go down. Here's a visual where we can see that process play out. The yellow area inside this chamber right here represents the gas. As the volume is decreased, you can see it dropping there. Just watch what the temperature gauge does. As the volume goes down, temperature goes down. As the volume goes back up, the temperature goes back up. Graphically, we can see that here. The line increases in this direction because as the temperature goes up, the volume also goes up. The mathematical equation behind Charles' Law is V1 over T1, so it's divided by T1, equals V2 divided by T2. Of course, the ones indicate these are the initial temperature and initial volume of the gas before any change takes place, and V2 and T2 will be the final temperature and volume of the gas after a change takes place. The statement and the equation are the key ideas for this video, so make sure you pause, take a moment, and write them down. We'll close the video with two examples using the mathematical model associated with Charles' Law. In example 1, we'll take a look at a balloon that's being placed in a freezer and shrinks in size. Let's clear some space to work this out. So first, let's read through the problem and label each number as a V, T, or P so I know where to use it in the equation. First, it says the balloon is inflated to a volume of 0.75 liters, so that's a V. At room temperature of 27 degrees Celsius, so that's a T. Those are probably V1 and T1, but I'm not quite sure yet, so let's read on. It is placed into a freezer where the temperature decreases to -11. Okay, so here's a temperature, and it's decreasing to that, so that must be my T2, which confirms my original thought. Those are the T1 and the V1. The question says then, what is the volume of the balloon? So I'm solving for V2 when it goes into that freezer. Also notice the pressure inside the balloon remains constant. We need that to be true in order to use Charles' Law. Now before we plug these in and do any math here, there's two important statements we need to be aware of. The first is that just like with our last gas law, you can use whatever units you want as long as they match on both sides, with one exception. In Charles' Law, the temperature that you have to plug in must be in Kelvin. So in this question, notice I'm given temperatures in Celsius, 27 and -11. I can't use those. I have to first change the Kelvin temperature into Celsius with this equation right here. So let's plug in some of these numbers. My V1 goes on top, that we said was 0.75 liters, so 0.75 goes on the top of the fraction. Dividing that by T1, which is 27 degrees, but remember first I've got to change that Celsius into Kelvin. So take your Celsius temperature 27 and simply add 273 to it. That gives me a temperature now in 300 Kelvin, and since I've converted it to the proper units, the Kelvin temperature is what gets plugged in on the bottom. Now we can fill out the other side of the equation. V2, I don't know, that's what the question is asking me to solve for, given the T2 of -11, but remember that's Celsius, so I've got to take a moment and change -11 into Kelvin by adding 273. This gives me a Kelvin temperature of 262, which is the number I have to plug in to my equation since it's now in Kelvin. Now we've got a fraction here which complicates the algebra a little bit, and there's lots of ways you could solve this. I highly recommend anytime you've got fractions like this to cross multiply. Cross multiplying is going to get rid of the fraction so we don't have to worry about any complex algebra. That means my V2 is multiplied by the bottom of this fraction, so V2 times 300. So these are the results of my cross multiplying. and that equals the top of this fraction times the bottom of this fraction. So my 0.75, and I'm leaving out the units now because I know that they all match, so it doesn't really matter. 0.75 times the temperature on the bottom, 262. You can use whatever algebraic steps you like here, but cross multiplying is the best surefire way to solve it. Now I've got no confusing fractions to worry about. I just have to get V2 all by itself on one side of this equation. So if I divide both sides by 300 on this side as well, it'll cancel out 300 here, and I'll be left with V2 equals, with one final step, multiply those two, divide by 300. So I get an answer of 0.655. Since the units will match on both sides, my V1 was in liters, my V2 will also be in liters. Here's a second example about an empty plastic water bottle. Let's clear some space and look at this one as well. So reading through the question, it says there's 225 milliliters of air. This 225 is a volume, and that's inside the bottle at 18 degrees Celsius. 18 is a temperature. Not sure if those are V1 or T1 yet. Let's read on. Over the course of the day, it heats up in your car and increases in size to a volume of 350. So here's my second volume, and it's increasing to that. So that's my V2, which makes 225 my V1, and 18 degrees Celsius my T1. The question says, what temperature in Celsius was reached inside the bottle? Now I can start plugging those numbers into my equation. Here's my V1 and my T1, 225 over 291. Notice 291 is the 18 plus 273 to put it into Kelvin. And on the other side of the equation, we've got V2 over T2. I've plugged in already my 350 milliliters for V2. The next step will be to start solving this. I'm going to again recommend cross multiplication. That'll get rid of the fraction. So I'll have T2 times the 225 equals 291 times the 350. And after cross multiplying, we get an expression that looks like this. Now there's no more fractions, so all I've got to do is divide both sides of this by 225. That will cancel off 225 here and leave me with just T2 on one side of the equation, which is great because the problem's asking me to solve for that T2. Only thing left is to actually do the math. 291 times 350 divided by 225. And when I do that math, I get 452.67. Let's label units on this. Remember, they match on both sides. Since my T1 was Kelvin, this will also be Kelvin. It also introduces the last little trick in this question, and you've got to watch out for this, especially with Charles's law. The question did ask for temperature, but it asked for the temperature in Celsius. So when I solve for that T2, it is correct, 452 Kelvin, but it is not in the units that the question wants. Since it asks for Celsius, I've got to take that Kelvin temperature and convert it back to Celsius. And the way to do that in reverse is, instead of adding 273, we're going to subtract out 273. So my final step to get the exact answer as the question wants it is 452 minus the 273 to give me an official final answer in the correct units of 179.7 degrees Celsius. I've rounded off the 0.6 a little bit there. And that wraps it up for this video on Charles' law. Here's a brief summary.